Today we're going to talk about factoring polynomials and solving polynomial functions by factoring. Here are some special factoring patterns. For sum or difference of perfect cubes, here is how it factors. This is one of those forms you're going to have to memorize. You cannot use one of your usual methods for factoring. You have to know this formula. It will pop up on exams and in later math classes. However, it helps you to memorize it. I know our first binomial is cube root of the first term, cube root of the second term, and keep the sign in between. The trinomial afterward looks a lot like a perfect squared trinomial expansion, but it's missing that too. Another thing you could remember is that the first term of the trinomial is the first term of the binomial squared, the last term of the trinomial is the last term of the binomial squared, and the middle term is the product of a and b. To memorize your signs, you will always have 1 minus and 2 plus. So if you are factoring the difference of perfect cubes, your 1 minus will be in your binomial. But if you're factoring the sum of perfect cubes, your minus sign will be sandwiched between the other 2 pluses. Quadratic form is when something looks kind of like ax squared plus bx plus c, except this time it's au squared plus bu plus c, and u is a function of x. For it to be in quadratic form, the middle exponent needs to be half the largest exponent. So you could have something like x to the 6, x to the 3, and then a constant. X to the 8, x to the 4, and then a constant. X to the 10, x to the 5, and then a constant, and so on. As long as the degree is an even number, the exponent of the middle term is half the degree, and the term at the end is a constant. Then you know it's in quadratic form. Begin by factoring x to the 8 minus 20x to the 4th plus 64 completely. Wow, look at this. We have x to the 8, and then x to the 4, and then a constant. This is in quadratic form. There are two ways you can factor quadratic form. First, I need to notice that it's quadratic form, and then I'll try to figure out what two numbers multiply to give me 64 and add to give me negative 20. Those factors would be 16 and 4. To add up to be negative 20, it would need to be negative 16 and negative 4. Now when we write our factors, they are no longer linear factors with x to the 1 times x to the 1. What multiplies to give me x to the 8 would be x to the 4 times x to the 4. When we multiply the same base, we add the exponents. Include your factors of negative 16 and negative 4. Now you've factored using quadratic form. How else could we do it? We could factor quadratic form by substituting u. Notice that the function of x of the middle term would be u. So u would be x to the 4. And now you would rewrite this trinomial in terms of u. So it would be u to the 2 minus 20u plus 64. When you factor this, you would get u minus 16, u minus 4. Then you could substitute x to the 4 back in and see that you get what we got over here. Now, am I done factoring? Well, no. I actually noticed something special. X to the 4 is a perfect square. It is x squared squared. And 16 is a perfect square. It's 4 squared. And we're subtracting, so it's difference of perfect squares. So this first binomial will factor to be x plus 4, x minus 4. Oh wait, not just x, the square root of x to the 4. So x squared. This binomial is also difference of perfect squares. So I will expand this one to be x squared plus 2 times x squared minus 2. Are we done factoring? Anytime you have a binomial with something squared, always look for if it's difference of perfect squares. X squared minus 4, that is difference of perfect squares. X squared minus 2, not difference of perfect squares. Or at least not difference of perfect rational squares. X squared minus 4 is x plus 2 times x minus 2. Now have we factored completely? Yes. I have no difference of perfect squares, I have no sum or difference of perfect cubes, and anytime you have a linear factor, like x to the 1, you've definitely factored fully. This is not an equation, so we don't need to use the zero product property to solve. Let's try factoring x to the 7 minus x. What do you notice? First and foremost, take out the GCF, the greatest common factor. X is in common with both of these terms, so I'll take out x. That means dividing each term by x, which would get x to the 6 minus 1. What do you notice about x to the 6 minus 1? X to the 6 minus 1 is difference of perfect squares. The square root of x to the 6 is x cubed because x cubed squared is x to the 6, and the square root of 1 is 1. This would be x cubed plus 1, x cubed minus 1. Now we have factors with cubes in them. Let's check to see if we have perfect cubes. X cubed is a perfect cube, and yes, 1 cubed is 1. So begin by factoring x cubed plus 1. It should become a binomial times a trinomial every time. Begin with the cube root of x cubed and the cube root of 1 and drop your sign. We're always going to have one negative, and if it's not in the first binomial, it should be in the second trinomial. The first term of our trinomial should be the first term of the binomial squared. The last term of the trinomial should be the last term of the binomial squared. And the middle term is always a times b, 1 times x. Now factor x cubed minus 1. You should have a binomial times a trinomial. If this is a cubed minus b cubed, in here should go a minus b, so x minus 1. In our trinomial, we always have one minus sign, so these need to be plus signs. The first term is the first term squared, the last term is the last term squared, the middle term is this times this. And there's our full factorization. The fundamental theorem of algebra states that if p of x is a polynomial of degree n greater than or equal to 1, then p of x equals 0 has exactly n roots or zeros, including multiple and complex roots. So the degree of the polynomial gives you the amount of solutions for the zeros of the polynomial. The polynomial f of x has a factor x minus k if and only if f of k is 0. You only have a factor x minus k if k is a 0 of the polynomial, meaning plugging in k gives you a result of 0. That is the factor theorem. For number 2, we're going to solve by factoring. What do you notice? We just factored this problem in number 1. So go ahead and copy down your factorization for part A. Because the degree of the polynomial is 8, this problem will have 8 zeros, or roots, or solutions. So now that it's fully factored, let's use the zero product property to solve each factor. Now remember, plus or minus means two answers. So here you have positive 2i and negative 2i, negative 2, positive I root 2 and negative I root 2, positive root 2 and negative root 2. How many solutions is that? 8. Some of those solutions are real, some of those solutions are imaginary, but all of those solutions are complex. Because complex numbers include real numbers, imaginary numbers, and real plus imaginary. For part B, we also factored this in number 1. So go ahead and copy down your factorization, and then we'll use zero product property to solve. Now this trinomial may look like it is factorable, but guess what? If it was factorable, I would have given you the factored version when I gave you the formula. The trinomial that you have factored from a sum or difference of perfect cubes will never be factorable. You must always use completing the square or quadratic formula to solve this trinomial. Because b is not even, I'm going to use quadratic formula. Fortunately, you have a bunch of 1s, so go ahead and simplify. Continue using the zero product property. And use quadratic formula for this one. Time to check if we have all the solutions. The degree of this polynomial equation is 7, so we should get 7 complex roots. X equals 0, x equals -1, x equals 1 plus I root 3 over 2, x equals 1 minus I root 3 over 2, x equals 1, x equals -1 plus I root 3 over 2, x equals -1 minus I root 3 all over 2. That is 2, 4, 5, 6, 7 roots or solutions. So there are your answers. Try part C on your own and then press play when you're ready to check your answer. Now you may be tempted to at this point in time use the zero product property, but guess what happens if you do that? You get one answer from x cubed minus 8, but x cubed minus 8 has 3 solutions. This factor should give us 3 solutions, and this factor should give us 3 solutions, so that in the end we have 6 complex solutions, or zeros, or roots. This is difference of perfect cubes. Wait a minute, I have a repeat. I can write this as x minus 2 quantity squared. And another repeat. I can write this as x squared plus 2x plus 4 quantity squared. You may have noticed that we had a repeated quantity in our second step, but I didn't want us to get confused while factoring, so I waited until now to write those as quantities squared. So now when we use the zero product property, x equals 2 is a 0 with multiplicity 2. So x equals 2 is actually 2 of the 6 zeros or roots that we need to find. Now use zero product property for this trinomial. Remember, because this trinomial is quantity squared, its solutions will each have multiplicity 2. This one's actually a great candidate for completing the square, so I'm going to do that. Which makes our 6 solutions x equals 2, multiplicity 2, x equals -1 plus I root 3, multiplicity 2, and x equals -1 minus I root 3, multiplicity 2. Because of the multiplicities, we found all 6 solutions.